Hey, Physics 20s, I'm going to go over this practice final here. So, yeah, let's get at it. So, which quantities are classified as vectors? So remember that a vector is a quantity with magnitude. I could write this out. Magnitude and direction, right? So quantities that would make sense if you put a direction on the end of it. That would be good. Well, these ones here, you don't have like things like mass and temperature and stuff. Those are obviously scalar quantities. But here we have some things that are kind of look like they could be scalar or not, like distance. Distance is a scalar quantity because the displacement is its kind of counterpart for that, right? So distance doesn't count. Position does, and velocity does. So those two things have direction to it, like your position could be the east or the west or the right or left. So that one counts, and displacement counts, but speed doesn't. Speed and velocity are kind of the counterparts to each other. So I'm just going through, I'm just crossing off things here. I notice that each one of these has one thing that's not right, but this last one, you can't see it behind my head, says velocity. So D is going to be my answer. Okay, so we got a bus here traveling 90 kilometers per hour north, and then it's traveling 105 kilometers per hour south. What is the average speed? So very key on this question, we're looking for speed. I'm going to do this two different ways, just to show the difference between them, because there is a difference between finding the speed and the velocity. So my first one is what they want. They want to find the speed. So to find the speed, I'm just going to go take my distance I travel and divide it by time. So I need to find the distance you travel. So what I'm going to do is I'm going to split this into its two parts here. The first part, the 90 kilometers in the north direction, and the other one is in the south direction. So the 90 kilometers per hour for 1 hour, how far have I traveled, right? So if I multiply those together, I've traveled 90 kilometers in the north direction. Right? I'm just going to write that over on this side here. Actually, I'll do that later. And then here, I'm going 105 kilometers for 2 hours. That makes sense. I'm going for 2 hours. I've gone 210 kilometers. So overall, I've gone 300 kilometers, and I've done this for 3 hours. All right? So if I do my V is equal to D over T here, let me just erase that line for a second, then I'm going to have 300 kilometers divided by 3 hours. That's going to be 100 kilometers per hour. So that's my answer, 100 kilometers per hour. No direction, because speed is a scalar quantity. But if I want to say that, what is my velocity? So say I was going to do this a little bit differently and find my velocity instead. Now this is beyond the question. You don't have to find this. I am still going to do D over T, but this time my D is going to be my displacement because I'm going to care about direction. Now when I'm adding my displacements together, one is north and one is south. So I'm going to be going, rather than just literally adding 90 plus 200, I'm going to be going, let's just say north is positive. I'm going to be going 90 kilometers plus a negative 210 kilometers, still over 3 hours, right? So I would go 90 minus 210, and I get negative 120 over 3 hours. So I have an average of 30 kilometers per hour. What's the negative stand for? Because I said north is positive. This means it's going south. So my average velocity is 30 kilometers per hour in the south direction. That's a little bit beyond the question because all I really cared about is what is this speed here. So not that one. All right. So I'm going to be the 30 kilometers per hour. Cool. Okay, let's look at this next one here. We want to know which one is a uniformly accelerated motion. So which one is accelerating here? Well, I'm going to just kind of cross off some graphs that don't make any sense. Here my velocity is changing all like in one instantaneously. That doesn't really work too well. technically accelerating, but acceleration with an infinite acceleration here. So remember, acceleration of a velocity time graph is the slope of a v velocity time graph. So if I want a uniformly accelerated motion, I want my slope to actually be something and not curvy. So this one here, kind of going off in a nice straight line, has a nice constant slope. Right? Because there's a nice constant slope, constant acceleration. Right? So this is a good one. Now, this one here, its acceleration is 0. I guess that is uniformly accelerated motion. Its acceleration is 0. I think they're going with this one here. Here, my acceleration is 0. I guess that kind of counts. Here, my acceleration is always changing. Or I got constant speed. My speed is always changing here. My acceleration is always changing. I can do like tangents here. And with the slope of an instantaneous, if I want to find instantaneous slope, I find those tangents. So if I were to do a tangent here, and then do a tangent here, and then I do a tangent here, you can see those slopes are always changing. All right? So one versus the other. There. All right. Let me just fix that up a little bit. Okay. So, not that one, not this one for sure, maybe this one, but I would say B is my answer for this one. Next one, I want to know what my uniform accelerators. So these little spark tapes, how they work is that the dots are always going to be the same time apart from each other. Like this is 1 second, then 1 second, then 1 second. And if I want to have uniform accelerated motion on a displacement time graph, because that's what these kind of represent, I want a nice curved graph if my acceleration is not going to be 0. Okay. So if I want to be accelerating, I want that nice curved motion. So I want the distance to always getting bigger and bigger and bigger. So this looks good, right? Now here, it starts off the same and then it skips something and then it starts off the same and then nothing after that. I don't like that. This one here just seems like the same, then skip. I want that to always be increasing. So A is a better answer for that one. What type of motion is represented by this here? So we've got a velocity time graph. It looks like it's going from the positive into the negative. An object is pushed horizontally, it comes to a stop. Well, it does come to a stop, but then it keeps on moving, right? An object's pushed horizontally on the ground and finally speeds up. It is speeding up after it crosses over the x-axis, the negative realm, which just means it's going backwards. It's tossed vertically in the air and falls back down. Kind of like that one because it starts off fast, it's slowing down to a 0, and then as it comes back down, its velocity is negative because down, like this is up, this is down, or west, east and west or something, but they're opposite directions. So I like that answer. Here it comes to a stop, but it keeps on going. So I don't like that one. Object dropped vertically, reaches a point of, it's dropped, it would start at 0. But here, this is where it stops. Okay. So it's going up, but slowing down, comes to a stop, and then speeds back up. I kind of like that. C looks good. Okay. The graph describes the motion of an object that is initially moving west. So this object is initially moving west here. Let's see if it's initially moving west. So down here it is west. All right. So negative is west. So that means positive must be east. Okay. So that's going to help me out with my direction later. The object moves a distance between 8 and 14. So the distance of a velocity time graph, distance or displacement is the area under this graph because it's a velocity time graph. So I want to know the area of this shape here. So there's a couple of different ways. I could split it into multiple sections. I can use the trapezoid formula. I could do a few different things. Say I did this in triangles here. I have 2 triangles that are the same, and then I got this rectangle in the middle. So the rectangle in the middle is 2 by 20. So I got a 40. Let's just call that section 2 1 and 3 here. So let's do section 1 first. So section 1 is a triangle. So it's 1/2 base times height. Nothing weird with my units. Velocity is meter per second. Time is in seconds. So I got 20 by 2. 20 by 2. And that's 20, right? Section 2 is going to be a 20 by 2, but not halved this time, so just a rectangle. 20 by 2, that's 40. And then section 3 is also 20, right? So it's going to be the same thing, 1/2 base times height. Okay? And then I add them all together, and we get 80 meters. Okay, so what is the acceleration here? So remember, the acceleration of a velocity time graph is the slope. So I'm going to want to find the slope of this graph. So at the tangent at this 2, at the 2 seconds, because remember, to find instantaneous slopes, you want to find the tangents. But the thing about the tangent of that line, it just happens to be the slope of that line. So to find the slope of that tangent, it's pretty easy. You just find the slope of the line that's on. So I can find anywhere. It's just a nice long line. I find 2 good points on that line. So let's say I found this beginning point and the end point here. And to find the acceleration, I just want to find the slope, which is going to be rise, my change in my velocity, over the run, which is my change in time. So if I'm using my 2 dots there, my final is going to be 10 meters per second minus, I'm going to use my initial of negative 10 meters per second. And I got a time of 4 seconds minus 0 seconds. So here I got positive 20 meters per second over 4 seconds, which is 5 positive meters per second squared. Because it's positive, and we decided this before, since they said it was initially going west and west was negative, then this must be east. So it's 5 meters per second squared east. There you go. Let me just write that down here, east. All right, so we got a ball here. It's undergoing uniform accelerated motion. It changes the velocity from 20 east, so 20 east to 10 west in 32.5 meters. How much time has passed? Okay, so it undergoes acceleration, so that means I'm going to have to know, well, just something's messing up here. Okay, I'm going to have to know 3 of these pieces of information. So I want to find time, so that's one piece I can't have. I have distance, so that's nice. 32, and it says going east here. So let's say east is positive. All right, so that's going to be nice and useful because we want a sign convention because I got opposite directions here. I've got an initial velocity of 20 meters per second, but my final velocity is going west, so that's minus 10 meters per second. So finding a formula that has these 3 things in it. D is equal to, and this one I don't use that often, VF plus VI, yep, that's the one. VF plus VI over 2 times T. I'm trying to solve for T. Okay, so I can rearrange this. I can put the numbers inside the brackets and find that number and divide it over. I can just times the 2 up to the other side so that I have this instead. And then divide over that larger set of brackets there. Lots of different ways to do it, but it's up to you. You can get the same if you just put the numbers in first and then rearrange it. Yeah, so yeah, why not? 32.5 divided by times 2. So 32.5 times 2. So I'm not going to put most of these numbers in here. I'm going to add these together. So I'm adding a negative. So it's like I'm minusing it. So I get 6.5 seconds. I want 3 sig digs here. So 6.5 meters per second there. I just want to get my other answer key out here so I can just confirm that I'm doing this correctly here. Okay. Or at least getting some of the same answers we had before. All right, so questions 6 and 7 here. Well, what we're going to do is we're going to start off with questions 6 and 7 because this is going to be a T-chart question. I'm trying to find that max height. All right, so max height means that my VF vertically is going to be 0. So that's something to do with my T-chart. We'll come back to that in a second. So right now, what we have here, we have the hypotenuse, and I'm going to go down here and I'm going to create my T-chart, and I'm going to talk about where I'm going to put some of these numbers here. Okay, so in our T-chart, we have two parts, right? We got the X side, we got the Y side. The X is the horizontal direction, and the Y is the vertical direction. I'm just going to say up is positive there. I'm just going to say this way is positive over here. Yeah. So in the vertical direction, we have a few things that we know. We know that the acceleration is going to be negative 9.81 meters per second squared. If I say up is positive, acceleration is down. Horizontally, there is no acceleration. The only thing I'm allowed to do here is just talk about like v is equal to d over t. If there's no acceleration, that's the formula I have to use. But in the vertical section, I'm going to need to know, because in this case, I want to know a few of these things. And down here, when I'm trying to find the maximum height, right, I want to know the d. So I'm going to need to know these things. So I've got to think of, where does that 85 fit? Well, the 85 doesn't fit in the chart. Remember, the chart is the x and y. It has nothing to do with the hypotenuse. Well, you can't put the hypotenuse in there. It has something to do with the hypotenuse, because what I need to do is I need to break this up into its x and y pieces. And then I could put those into that chart. So the x piece here, let's put that 40 degrees in there, is adjacent, so that's going to be cos 40 degrees. So I've got 85. And my y piece is across from here, so that's going to be sine 40 degrees. Okay, so then what you're going to do, I'm just going to write those down here. So in the x piece here, because this is a velocity graph, I'm going to put it into my velocity section. But there's no initial, there's no final, it's just a velocity because my speed doesn't change in the horizontal direction because there's no force. So here I got 65.113777, much more there. And when I'm going to do the same thing, I'm going to do the same thing with that one. I'm going to go sine 40 times 85. And this is going to be positive because it's going upwards, 54.636946 meters per second. Okay, so now that we have the components there, we just, I remember up here we said VF is equal to 0 because I'm reaching to my maximum height. So I put a little 0 there. And then I just find a formula that involves those four things, which is going to be equal to delta V over T. Here I want to solve for time, so I'm going to just rearrange this times the time up, divide the A down, and that, remember that delta stands for final minus initial. Okay, my final is 0, so I'm going to have 0 minus this number. And I'm going to divide by 9.81, and I'm going to get 5.57 seconds. So that's going to be B. Okay. Now here, maybe I don't trust that time, so I'm going to avoid the time. So I need a formula that doesn't have time in it. So here I had a formula that didn't have D in it. So our formula doesn't have time, but it still has the same other things. We're trying to find that maximum height, so we say VF still is equal to 0. So I'm going to be using this formula. VF squared is equal to VI squared plus 2AD. I'm going to put a 0 in this spot here, so I get a simplified equation that looks like this. I'm going to rearrange this for VI, so minus VI squared is equal to 2AD, and divide by D. So let's divide by D. So minus VI squared divided by 2A. Here we go. So I'm going to take this number that I have in my calculator. Well, I had in my calculator. Let me see if I can find it. That one right there. Yep. 54 number. I'm going to square it. I'm going to divide by 2 times 9.81. So you got to make sure when you divide by two numbers, put them in brackets, make sure they're actually dividing by two numbers. Find 2 times A and then just use the one number. Just make sure you divide by two numbers. In this case, I got 152 meters. There we go, another B. So I didn't have to deal with the horizontal section at all. Like if I needed to find the range, I could use the time I found and use it on the other side. But in this case, I didn't have to do that. A concept or principle explains why rapid braking feels as if she's being thrown forward. This is that inertia. This is the first law, right? An object in motion wants to remain in motion, right? Unless acted on by another force. So if you brake, the person in the car is just going to keep on moving forward, and they're going to be stopped by the seatbelt. It's going to slow them down because that's going to apply a force back. So they feel it on the seatbelt. That's the first law. Cool. All right, question 4. Numeric response number 4 here. A man pushes a refrigerator across level 4, must exert 200 newtons to maintain this. This direction here is just going to throw you off here. Maintain a velocity of 0.1 meters per second. When she stops, it's going to come to a rest. How long does that happen? So we're looking for time eventually. So to find the time, I'm going to need a few things. What's my VI? What's my VF? What's my acceleration? What's my D? All right, so my VF, it comes to a rest. It comes to a rest. So my VF is going to be 0 because it comes to that rest there. Okay, we don't know VI. Oh, I do. It's got a nice constant velocity here. Then you stop pushing, it's going to come to a stop. So it's going to start off with that velocity, come down to a 0. So I need my A or my D. So I'm going to find the A. And to find the A, I'm going to use this F net formula. F net divided by M. Right? What is F net? So if I were to draw a nice little picture of my refrigerator on a nice level floor, I got gravity pulling me down. I got my normal force pulling me up. I would have my applied force going this way at 200 newtons. And then because I'm moving at a nice, maintaining a constant velocity, I'm going to have a force of friction back at 200 newtons. So as soon as I break this, as soon as this disappears, this stays, right? So my F net is going to be this force of friction backwards, right? So let me just say that this way is positive, so that my F net is actually negative 200 newtons, right? And remember, F net is equal to mass times acceleration. So to find my acceleration, I'm just going to divide both sides by mass, and the mass is 500 kilograms. So that's a big refrigerator, right? Half a ton. Are they really that big? I can't remember. So negative 0.4. The negative is just saying that it's slowing down. It's a backwards acceleration. If I say forwards, it's positive. So I'm going to take that over here. 0. So this going over there. 0.4 meters per second squared. I'm going to find time. So I need an equation that doesn't have D. So we already have this one. A is equal to final minus initial over T. T is equal to final minus initial over A. And then just plug your numbers in. 0.1 divided by 0.4. So it's going to take me, or take the refrigerator, a quarter of a second to come to a stop. Cool. Okay, action-reaction pairs always occur in pairs, but they do not always result in net forces because they act on different objects, right? So action-reaction have to be on different objects. So when you do your scope, sometimes that other force is actually not on there. So like this calculator has a force on it. So if I drop it, it's going to fall down. Then the Earth is going to come up at it. But because we're looking at this scope, it's going to have its own acceleration. The Earth is going to have its own acceleration based on the masses. So very key. Sorry, these are different objects. Okay. Next one, we got a cement block at rest. So that's my A is equal to 0. That means my F net is equal to 0. That means everything in the X and the Y have to add up to 0. Okay, so if I draw all the forces that I have on here, what's holding this block to rest is my friction. I got that normal force because it's going to hit the desk and the desk is going to push back, or the plane is going to push back. So these three forces have to add up to 0. Now, rather than deal with X and Y's in this nice perpendicular direction, what we can do with our X's and Y's is we can kind of put them at an angle instead, because we want our direction of motion to be on one of the axes to make our lives a little bit easier. Because if the force is not in the direction of motion, then the force must cancel out. So like this Y component of gravity has to cancel out with that normal force. So what's actually keeping this in motion here, or keeping this still, is actually that friction force. How do we find it? Well, if everything in the X direction has to add up to 0, that means the friction force plus this gravitational force that's acting down the hill. So not all gravity, because part of it canceled out with the other one. They had to add up to 0. So if I can find gravity, which is going to be equal to mass times, or so the gravity in the X direction, right? It's going to be mass times gravity times sine 30. So if I put my 30 degrees is going to be inside here, right there. That's going to be my 30 degrees. So it's across the triangle is the X. So it'd be sine. So I can punch this in a calculator here. What is this? A 20 kilogram block times 9.81 times sine 30. So I get 98.1 newtons. It's equal to my force of friction. We're just worried about the magnitude here, because that's what we want here. So this is going to be 98.1. You can put that in here if you want to. All right. For a test mass, which of the following graph represents gravitational field strength versus the distance from the Earth? So I'm going to go with this one that's a little bit steeper, because this is 1 over r squared. 1 over r has a kind of a nicer curve to it. These ones just don't make any sense. Okay. So this is an inverse square law. Okay. Let's skip past that. Statement about a car around a curve. Okay. When a car is on a horizontal curve at a constant speed, which of the following is true? So 2 is true. Net force is not 0, so this net force is going to be something. Maybe my net force is probably going to be like my friction on my tires. So that's not going to be 0, so that's not true. So I'm going to cross everything that has a 1 on it. There we go. The acceleration is constant. That's not true either, right? Because the acceleration is always changing. So it's got to be 2. There you go. You could draw a little picture here if you want to. Here's my car. This is a top-down picture. There's got to be this friction force acting inwards to keep the car in motion in that circle. Okay, so here we got a cyclist pedaling at a frequency of 90 RPMs. If the distance from the pedal to the axle is 24 centimeters, what is the centripetal acceleration? So remember, centripetal acceleration, we have 2 options, right? We have v squared over r or 4 pi squared r over t squared. So depending on which one we have, which one are you going to use here? So what do we have? We have frequency. So that means technically we have periods. Remember, frequency is equal to 1 over period. And if my period is 90 RPMs, so it's going to be 1 over 90 RPMs. So this is going to be 1 over 90 minutes. All right, so this is going to be, because this is RPM, so when I do this, I'm going to get this in minutes. So I want to change this to seconds, so I'm going to times it by 60. So I get 0.666 seconds. Okay. So now we have the period. Now I can go over here, got the radius. Yeah, okay, so I can find my acceleration. So my acceleration is going to be 4 pi squared r over t squared. Just making sure I change the r, 24 centimeters, to 0.24 meters. Right? So 4 times pi squared times 0.24 divided by period squared. And I get 21.3. There we go, 21.3 meters per second squared. Cool. Okay, so this frequency, or is a radius of 42 centimeters this time. Traveling at a speed, what is the frequency of rotation of its wheels? Okay. So here I want to find t, right? Because frequency is going to be 1 over t. So if I can find t, I can find the frequency. I want to find seconds here, so I'm going to change some of these numbers around, right? So 90 kilometers per hour is the same thing as 25 meters per second. This is just me dividing by 3.6. This number here is 0.42 meters. So make sure you change that. And we can find the period by using this formula. Now, this one here is very overlooked most of the time. So times the t up. A lot of people want to jump to those other ones because they seem more exciting, but this is probably the best choice here. So I'm going to go 2 times pi times my radius divided by my speed. So I get 0.105557 seconds. I'm going to go over here and go 1 over this answer. So we get 9.47 hertz. Perfect. There we go. Okay. The moon Ariel orbits Uranus at an average radius of blah, blah, blah. If another moon, Titania, orbits at a different radius, what is its period? Okay. So there's a couple different ways to do this question, but I think the best way to do this question, because they're both orbiting the same object, Kepler's third law should apply here. So this formula is on your formula sheet now. I can put the information here. So this side would just be one object, this would be another object. As long as they're orbiting the same thing, in this case they're both orbiting Uranus, I can put the two numbers in here and then cross multiply divide. So I got my period for one of them. Make sure you square that. Then I got my radius for that same one. And then on the other side, I'm going to put the radius, my new radius. So it's got a larger radius, so it's probably going to have a larger period. But it's not like directly proportional. It's not like if I double one, I get double the other. Because these cubes and squares, everything's all messed up here. And we're just looking for this period squared. So I'm going to cross multiply divide, making sure to take that square root. All right, cross multiply divide, take the square root, and let's see. This is cubed. 5 squared divided by 1.918 cubed. Take the square root. Blam. Okay, so if I did that, I get 751,000, sorry, 858. And because I put seconds in, I get seconds out. Let's put that in proper sig digs here. So 7.52 times 10 to the 5 seconds. And the way they have this written out here, A, B, C, D. So if I were to put these in boxes here, they'd want the 3 sig digs, so 5 or 752, and then they want their exponent as a 5 there. There you go. Ignoring friction, how much work would be done to lift a car, elevator car, from one floor to another? Now I'm assuming that we're stopping. Okay, so one floor to another. So my change in my energy, which is going to be the change in my kinetic plus my change in my potential. That's going to become my work, right? My work energy theorem. So if I come to a stop from one ground to another ground, I'm making this assumption that this is 0. So my work is just my change in my potential, which is going to be my potential final minus my potential initial. We can calculate those two things by going mg_hf minus mg_hi. So we can find that work. So mass times gravity times that change in height there. We get 482,063.4 joules, because all the units are nice. We got meters, we got kilograms, we're all good there. So we're going to end up with C here. Not bad. Okay, skateboarder comes down a ramp, coasts along a level road. At the bottom of the ramp, it has an initial speed of, I'm just going to write some of this stuff down, 4.92 meters per second. After a certain amount of time or distance there, it has a final speed, and it covered a distance of 35 meters. What is the work done here? All right. So what I'm going to want to do is I can go force times distance, or I can just find the change in the energy here. So my change in my energy, which is just going to be, I'm assuming if my height doesn't change, a nice level roadway here. So my delta EP 0, then the only thing changing here is my kinetic energy. So that's going to be 0. I just have to find my final kinetic energy minus from my initial kinetic energy, 1/2 mvf squared minus 1/2 mvi squared. You just do that calculation really quickly here. 1/2 times the mass, 68.4 times the final velocity squared minus the initial velocity squared. So I get 700, technically negative 787 joules. The reason it's negative because you lost that kinetic energy by loss due to friction. Yep, loss due to friction. Cool. All right, so let's use this. This is a force position graph here. So this looks like it's obeying Hooke's law. It's a nice straight graph. It's got a nice constant thing here. If I want to find the slope, I can find that slope. Do I want to? No, I don't. Because what I'm going to do here is I'm just going to blah, because force times x, like force times distance, is going to equal work, energy. So if I can find this area, I'm going to get energy. If I want to find the k, I could do that. And I could use the 1/2 kx squared formula to do that. But that essentially came from this. So the area of this is just going to be 1/2 base, so 15 times 10 to the negative 2 meters times height, 65 newtons. And there we go. So 1/2 times 65 times 15 times 10 to the negative 2. So watch out for those units, right? So 4.88 joules. So this times 10 to the negative 2 was pretty important there. Otherwise, it'd be 488, and we got the wrong answer. So be very cautious about these units here, right? All right, cool. Okay, you're pulling on a sack of potatoes here along a level floor. You're able to sustain a power output of 0.45 kilowatts. It's very key, kilowatts, for the time a potato to move across 46 meters. If the force required was 35 newtons, then you will take blank seconds to solve this question here. Okay, so power. What is power? Well, power is work divided by time. And what is work? Well, work is force times distance. So if I want to find time, I'm going to times the time up to the top, divide the power down, and then I just put all the numbers in. All right. So we got our force, we got our distance, we got power. So you can see that I'm going to change the units so they're not in scientific or in kilowatts there. So that, honestly, that didn't have to be in kilowatts. It's just 450. Yeah, it's just 450. It's kind of weird. I don't know why they use those units. So 36.2 seconds. All right, let's try the next one out. Pendulum bob here is pulled sideways. Its length is that, blah, blah, blah. So I'm going to solve this question. What am I going to do? What's the kinetic energy as it passes through the lowest point? So it has a length of this. It's pulled sideways until it's 30.8. So this height here, 30.8 centimeters, oops, above the ground. I'm just going to change that to meters. So that's its height. So when it gets to the top there, and then let go, it's above its rest. So at the top here, its speed is going to be 0, and then at the bottom it would have its maximum kinetic energy. So here, my EK is 0, but my EP is at a max. It's the highest it's ever going to go. But down here, we're at a max kinetic energy, and that's what we're looking for. What's this max kinetic energy down there? So using conservation of energy, and if I just say that down here is my reference point, then my EP is 0 because we're at our reference point here. So I could just use conservation of energy, right? I could say that because all we have here is gravity, that work is equal to 0, or I could just say the mechanical energy that I start off with is going to be equal to my mechanical energy that I end up with, right? The reason behind that is I can say that, oh, there's only gravity, so work is equal to 0. Remember, work is change of energy. That's equal to my final minus my initial. So if I move this around over here, I can say my final is equal to my initial. Now, how do you find mechanical? Well, that's going to be EP. Uh-oh. Sorry about that. That's going to be EP plus EK is equal to, oh, I want to say it's not equal to, it is equal to my EP plus my EK. This is the final one. This is my initial one. And then I can just start putting zeros in. So I'm trying to find the final EK. My EP initial here is 0. My EK initial is 0. So all I have here is my mg initial height, and that's equal to my EK final. And remember, this is vertical height, so I don't have to worry about like any weird angles. It's just literally straight up that point some meters. And I got, what is it, 2.5 kilograms times 9.81 times the height, 0.308. So I get oh, this is fun. What is this all about? Okay, there we go. I get 7.55 joules. Looks like a D there. Sweet. Okay, so we got a wave segment is moving left through the spring at the instant shown. Where is the speed the greatest? So these things are going up and down, up and down, up and down, just like in Hooke's law. You want to go, when you go furthest out, it's going to have to stop to come back down. So when it's furthest out, that's its lowest. And then when it swings past the equilibrium, it's going to go back down. So here, this is where the EK is at its max, right? So P and T. So since those are my maximum points, that's where they're going to go the fastest. because they're swinging up and down. The wave has this optical illusion where it's kind of moving to the left, but really the things are moving up and down. So remember, this is a transverse wave, right? The vibration is perpendicular to the direction of motion. Which listed point has the energy stored in the form of potential energy only? So yeah, so it'd be R and V. Those are where they're all kind of stretched out. My EKs are 0 here. My EK is 0 for both of these spots here. So R and V. Get another D. Okay, so you generate a wave stretched on a spring stretched on the floor by oscillating your hand back and forth at a frequency of 1.6 hertz. It's got to go there and back, right? Then the length of the string or thing, so you're going to have to divide it by 2. So I can find the total distance because it takes 2.6 to go there and back. So this is the total. So I could divide by time if I want to, or divide it by 2, but I'm not going to do that. So this is my total time. All right, so keep that in mind. All right. It has a nice little wavelength here, or an L of 1.5 this. It's got a little frequency of 1 point something hertz. So using these two pieces of information, and V is equal to F lambda, that's a lambda, sorry, I could determine how fast this wave is going. So I times them together and I get 2.4 meters per second. Then I'm going to take that over to this other side and say V is equal to D over T. Rearrange this for D and determine that it takes a trip that is 6.96 meters. Okay? And then, because this is the total distance, I'm going to have to divide this by 2. 3.48 meters one way. There and back. Sweet. All right, which of the following best describes the principles of superposition? Which of the phenomenons? So wave interference for sure, right? Those are like when you have two waves coming at each other. So anything with a 2 would be an answer. So it's got to be okay. That one gets rid of one of my answers. Echoes? Not really. That's just, it's a reflection. So that doesn't make, that's not going to help. All right. Universal wave equation? No, not really. Standing wave. So remember, a standing wave is that kind of illusion where the wave is just kind of going up and down. Doesn't look like it's moving side to side. But remember, that's because there are two waves coming at each other and they're interacting with each other, create the standing wave through interference. So it's got to be 1 and 2. There you go. Well, that was the only choice I had left there. All right. Hopefully that helped, and I will see you later. Bye.